Hello. So in this video, we are going to be going through how to compute rational functions and some handy tricks in sort of ways to make it less painful, especially when you get big numbers. So in general, you want to remember whenever you're dealing with sort of fractions with functions in the top and bottom, right, that you can't cancel terms unless the top and bottom are factored, right? So if you have, a bunch of stuff being added together in the top and bottom, you can't start canceling, you would have to factor first. And sort of as a general rule, if the numerator or denominator, either one of those isn't factored, and you're trying to compute sort of at a value or an expression, you really do just have to plug it in and sort of do all of the work in the top, all of the work in the bottom, and then divide it out at the end. Okay, so let's look at some examples. So let's say we have this thing here, right? We have the x squared minus 3x, et cetera, on the top. We have the factored thing in the bottom, and we want to compute f of 2. Now, we do have a factored bottom, but we don't have a factored top, which means we can't actually cancel out. So in particular, sort of you might be tempted to be like, oh, there's an x cubed and x squared. We'll cancel some of that. Can't do that, right? So because the top isn't factored, I could either try to factor it, or I could just plug in the 2 and compute, right? So if I just plug in the 2, which is what I've done here, right? For all the x's, I plug in the 2 everywhere, and then sort of crank through the machinery, put everything together. The top, I end up with 1. The bottom, I have this negative 2184. By convention, we pull the negative out front, right? So it's negative 1 over 2184. So this would be sort of the standard way to just compute all of this thing, right? We'd compute all the top, compute all the bottom, get our answer. Now, in this case, because the top is a 1, there wasn't sort of a nice way of dealing with the fact that we have a large number in the bottom. But let's look at another example. So here we have a factored form, and let's say we want to compute f of 4. Now, if we had a factored form where there were factors common in the top and bottom, right? If we had like the x squared minus 4 on the top and the bottom, I could cancel those out before I've even plugged in 4. It would make my life easier. So here, it looks like it's as sort of simplified as you can get, which is true in the algebraic sense, but as we'll see, there's some tricks that we can still sort of pull out of our sleeves in terms of the actual numeric computation. So as it stands, since I can't simplify any of the algebra part, right, there's no common sort of factors, plug in 4, compute stuff. But I'm not going to multiply the stuff together. I'm just going to compute each of the terms, each of the sort of individual factors. So if I do that, I end up with this thing here. So I have 11 times 12 times 17 over 9 times 57 times 68. Now I could multiply all those together. That would be a nightmare. Like it's doable, but ew, right? So instead what I'm going to do is I'm actually going to factor the numbers. So what I'm going to look at, like 11 is prime, I can't factor that, but 12, I can make that as 3 times 2 times 2. And I can do that for all of the individual pieces. And the reason I want to do that is that now I can think of this as sort of a factored form, but for numbers as opposed to the algebra at the top. And as I notice, there's a 3 here, there's a 3 here, there's a 2 squared there, there's a 2 squared there, there's a 17 here, there's a 17 here. Now I can cancel out a bunch of these numbers before multiplying all the stuff together. So I can cancel out those 2 squareds. And that way I don't have, right, that's a factor of 4 on the top and bottom, I don't have to multiply out. Can factor out, or factor out and cancel the 3 that's in the top and bottom. Same with the 17. So now I'm looking at just 11 over 3 squared times 19. 3 squared times 19, not super fun to calculate, but a lot easier than 9 times 57 times 68, right? So looking at this now, much easier to do. Do that all out, I get 11 over 171. And the nice thing about this is it's already in this sort of simplified form, right? I don't have any common factor on the top and bottom because that's exactly what I got rid of up here. Now in contrast, if I had just multiplied everything out at the start, that would have been 2244 over 34,884, and then I would start reducing that, right? And like, oh, they're both even, divide by 2, and work my way down slowly but surely. Much more of a headache, right? So it's a lot easier when you get sort of to a step like this, where you have a bunch of numbers being multiplied in the top and bottom, to factor the numbers or at least find common factors to cancel out, right? So you could have just looked at like 12 and 68 are both even, cancel a 2 from each of them, and that would have been equivalent, work your way through, okay? All right. So what we do? Well, we talked about computing rational functions and how if you don't have them sort of factored in the top and bottom, there's really not much you can do other than plugging in the number and working your way through it up to the point where you end up with numbers, right, in the top and bottom that if those are being multiplied, right, again, this is key, they weren't being added or anything, they were being multiplied all the way through. But if they're being multiplied all the way through, then you can actually break it up the same idea, right? Have the different factors, cancel the factors. That way you don't have to multiply a bunch of stuff together and give yourself a big headache, right? And at the end of the day, you have to do all of the top, then all of the bottom, and then you can try dividing the two. And if there's sort of commonality, right? If it ends up being 7 somehow, unlikely, but it happens, right? The division part comes last, okay? So that is that.